Polarization, as y'all have probably heard, has something to do with sunglasses. Why? Because sunglass lenses are polarized. Well, they polarize light, and we're going to understand a little bit more what that means later on. Basically, they filter out glare or unnecessary light waves from hitting our eyes. And so to understand more of this polarization, because it's not very clear yet, we have to look at a wave, just a basic light wave. And so we're going to use this wave as a representation for that. So this is going to be our light wave. And notice how it oscillates up and down, up and down. That oscillation is going to be important to understand how some light passes through a filter while other light doesn't. So I'm just drawing this arrow to show that direction of oscillation, which is vertical. And then propagation, which really just means kind of movement, the direction of the wave. Propagation is left to right for this particular wave. And so just keep in mind, propagation is direction or movement, and oscillation is kind of that for this example, that vertical kind of up and down uh, factor of the wave. And so since it's not super easy to explain just in words, we're going to use a little more visualization. But we're going to look at array next. An array is going to help us to understand how all these light waves kind of affect or can be polarized. Because what happens with a light ray, and we're going to say this is from the sun, for example. A light ray is just a straight line, and it's not exactly a physical thing. It's not necessarily tangible. It's kind of just a concept, kind of like the Earth's axis. It's just there to show us that light waves kind of have a center that they're like set on, I guess. And so we're just going to draw a couple waves here. This vertically oriented one and this horizontally oriented one, which is kind of hard to see. But essentially, array is made up of a bunch of, oh, I'm going to do that in a different color actually. Array is just kind of this center point around which waves oscillate. So let's say that blue is vertical, so it's going to have that vertical oscillation. The red horizontal, and let's say there's a diagonally oscillating one, another diagonal direction, and you really have no idea how many waves are going to be on this ray. It could be hundreds, it could be 10, I don't know. But lots of waves are on this single ray. And so that's going to kind of help us understand a little bit more of how glare works. When we look at kind of the reflection of water, like on a lake, on a really sunny day, we see a lot of glare because lots of different waves are kind of hitting our eyes, and without a filter to block out some of those waves, we're kind of just getting the full blast. That's why glare happens. And so what we're going to do next is look at this image of it's really just another visualization of what I just drew to make it a little clearer. So this is an image um, like one in the book, and it shows kind of what I was trying to explain, that some waves have different directions of oscillation than others. Like this red one is vertical as opposed to this blue one here that's horizontal, and kind of drew that in the wrong order, but yeah, so this black line, this C right here is the ray, and E and B are waves on that ray. The direction of polarization, as shown in this diagram, is going to be vertical. So we'll just follow along with that and make a little polarizing filter. But right before we do that, I'm just going to explain really quickly how a polarizing filter works. So polarizing, and it really just means kind of um, redirecting, I guess, or filtering almost, because which would make polarizing filter redundant. But Polarizing really just kind of makes certain waves pass through, certain waves not pass through. And so on a really microscopic scale, we're going to have this filter that looks something like this. And what makes the filter, um, sounds kind of funny. What makes it filter is that the molecules that make it up have this alignment. It's not necessarily vertical all the time. In this case, it is because that's what this diagram shows. So we're just going to follow along. But let's say it is vertical. And so the molecules are going to be, oops, that's ugly. They're going to be vertically aligned, making these kind of columns. And to make that a little clearer, we're just going to redraw this. We were going to anyways, but we're going to have this filter. Once again, it's going to be polarizing vertically. So we're just going to draw these little slits. And so what these slits do, which are really just those molecules, is that they only allow for waves that are oscillating vertically to pass through, like this red wave. And so we're just going to draw this red wave continuing on. So it's going like that, it's going like that. And oh no, it hits this filter, but it doesn't matter because it's oscillating in the same direction that the filter is polarizing in. So what happens, or where the problem really is for this blue guy, because he's trying to keep on going and going and going, but horizontal doesn't really match well with vertical, so he's just going to stop once he hits the filter. Um, and so that's how polarization works on a very basic level. I don't know it all, but that's the gist of it. So now we're going to take a look at Malice's law, which is pretty much just a law that explains why a vertically oscillating wave will pass completely through a vertically polarized filter, and why a horizontally oscillating wave won't pass through at all. But let's say a diagonally oscillating wave, so say our filter is like, oops, let me get the pen out. Yeah, all right. So our filter looks something like this, and let's just say that's vertical, even though it's not perfectly straight. And we have a wave that's oscillating in this direction, coming towards, propagating towards this filter. So what happens is some of this wave is going to pass through. I don't know exactly what that looks like, but some of it's going to go through. And that can be explained by Malice's law. And Malice's law um, just says that the intensity of a light wave after it passes through a polarizing filter is equal to the initial intensity times cosine squared theta. And this theta is the same theta that we see right here in this diagram. This theta shows and proves kind of that what we've learned in trigonometry, that cosine of 0 is 1. 1 being the largest value you can get for any given input for cosine. So when our direction of oscillation and direction of polarization are the same as they are in this case, or for a wave that's oscillating vertically here, all of that light wave is going to pass through the filter. And likewise, like we already said, anything with a greater angle than 0 is going to pass through either partially or not at all if it's completely horizontal or 90-degree angle. And so that's really just the basic idea of Malice's law. All right, so we're just going to do a quick summary of what we talked about in this video about polarization. So we talked about how light waves, kind of like these waves here, have a direction of oscillation and a direction of propagation. So that direction of oscillation, once again, is, oops, we'll get rid of that. Direction of oscillation, for example, for this blue wave is horizontal. It looks like that. Direction of propagation for all of these is forward, kind of towards us. And that is just really, really basic stuff. All that does is help us understand how these waves will interact with the polarizing filter, which is going to allow some light waves to pass through and other light waves to pass through partially or not at all. As we saw with Malice's law, these light waves are going to pass through as long as their oscillating direction and direction of polarization is at least maybe not exactly the same, but as long as it as is less than say 90 degrees. This wave right here would not pass through this filter at all. This red wave is going to pass through partially because it has a degree of less than 90, or it has an angle of less than 90 degrees. And Malice's law once again shows us that our intensity of a light wave after it passes through a polarizing filter is equal to this initial intensity times cosine squared theta. So if our input, or if our angle is 90 degrees, cosine of 90 is 0, so none of that light passes through. And on the other hand, cosine of 1, cosine of 0, which is the angle difference between this direction of oscillation and this filter here. So when we have a wave that oscillates same direction, polarization, that wave is going to pass through completely. And so that's really just the basic idea of polarization. Polarization means taking light that is scattered, like this image here, or like this little diagram here, and that's just like sunlight. It kind of goes all directions. It's got waves oscillating in all sorts of directions. But to put a filter on that, like a camera lens or like your sunglass lenses, that will stop all the light that we don't need, or a lot of the light that we don't need, and allow us to see more clearly. And so that's my video about polarization.